Welcome. We have learned something about the pumps and the various ways of analyzing their performances for the scale up. So, we shall be now taking up a few problems in a set of tutorials to see how to apply those principles for the various types of effects from the pumps. So, in this particular tutorial, in this lecture, what we shall learn about, we shall do some tutorial on the critical flow rate to avoid cavitation, then how to estimate the head developed by a pump, and how to estimate the pumping power, and how to select a pump. Let us come to the first problem. In this, it is stated that there is a centrifugal pump which is used to pump gasoline, and the specific gravity factor is given like this, 8.5 kilonewton per cubic meter, and this is the vapor pressure of the gas. This is pumped from reservoir A to reservoir some reservoir B, and here is the pump with us. So, the reservoir B is not shown here, we are just concerned on the suction side. So, we have to determine the maximum flow rate that can be delivered by the pump without cavitation, because we know that cavitation occurs only on the suction side and not on delivery side generally. So, we are looking only in the suction side, and we have determined the maximum flow rate which can be used without cavitation, and we can neglect the minor losses, and it is given that the available NPS required NPSH is 0.75 meter, and we have to figure out then what is the available NPSH. Okay. So, these are the required NPSH, and this is given by the manufacturer of the pump, and this is the atmospheric pressure, and diameter of the pump, this pipeline is given as 0.5 meter. This S stands for suction side, and the length of the pipeline is given as the 50 meter. So, this particular pipeline can be assumed to be 50 meter and with a 0.515 meter, that is 15 centimeter diameter, and the friction factor may be taken as this value. So, with these information we have to find out the maximum flow rate which can be used without cavitation. So, firstly what we do, we put all the data, the information given to us, and here is a particular thing, and here we see this particular liquid level is about 2 meter below the pump level. Now, in this any of these pump problems, what we have to do, we have to apply the energy balance or the first law of thermodynamics. So, in this energy, what we take, we take pressure energy, the kinetic energy, potential energy, and some losses in the pipeline. So, these losses may be minor losses or may be major losses. So, here we take the VA to be 0, because this cross section is quite big. So, the rate of fall of the liquid level may be neglected, and then this PA, this is whatever pressure is on this is the atmospheric pressure which is given, and here we put the PSN by gamma as the HSN, that is the pressure head at the suction side. This SN is the suction of the pump, and now we with this we put modify this equation, this particular equation, and we finally get the NPSHA as this. So, this is the available NPSHA which we have to find out, and we know that if available NPSHA is more than the required NPSHA, then there will not be any cavitation. So, to find this NPSHA, we have to find out the value, because we know all the values, we need to know the value of this HLS, and this HLS depends on the flow rate. So, whatever the flow rate is, that will decide the value of NPSHA, and that is how we can decide that what is the maximum flow rate that can be allowed. So, we write this thing as this is the major friction loss and this is the minor friction loss. So, this as per the problem, this will be neglected, and in this we have the friction factor, the velocity through the pipeline ds and ls, and what we generally do, that we plug in all the values here in terms of the as. Okay, and we find, because this is, and this q is not known to us, this we have to find out, and as can be found out from the ds value. Now, after plugging in the value of this as is nothing but the pi by 4 ds square. Okay, plugging the value, we get this relationship between the head loss and the flow rate. This q is the volumetric flow rate. So, here we put all these things and find that NPSHA. If you put this value here, we find NPSHA coming in terms of the volumetric flow rate. Now, in order to avoid cavitation, this available NPSH should be more than the required NPSH, and if you put this particular expressions here, we find that Q should be less than this. That means the maximum permissible flow rate of the gas will be liquid will be 0.046 cubic meter per second. We should not cross this. If you cross this, then we will be landing up with the problem of cavitation. So, this is the critical flow rate for the system. Next, we come to the centrifugal pump, and the problem in which a centrifugal pump is running at a speed of 1800 rpm and it is pumping water at 20 degrees centigrade. The gamma is given here. Gamma is what? The product of the density and the gravitational acceleration, and this is the velocity. And here you can see that it is pumped from reservoir A to reservoir B, and the difference in elevation is about 25 meter, and here the datum is given for the horizontal pump. Okay. And the suction pump is about 15 centimeter in diameter and 6.7 centimeter in length, and the delivery pipe is 15 centimeter diameter, this is length, and the piping system has 4 bends, 2 valves. So, all these bends and valves etc., these fittings will be causing some kind of pressure drop through the system, and whenever the pressure drop is there, the suction head will also change. Okay. And that means the NPSH will change, and the loss coefficient in the suction pipe is given to be this 0.1, and the pipe friction coefficient can be assumed to be this value, and we have to plot the HQ curve for this particular system, and we also have to determine the system flow rate, the head developed by the pump, and the pumping power. Now, let us put all the data which have been given to us first here, and we again consider this particular figure. And as I said earlier, that let us apply the energy balance equation to generate the H versus Q curve. So, we write this in a Bernoulli equation here as I described earlier, and here again we find that because both these 2 points, this 0.1 and 0.2, which are at the surface of the liquids in the 2 tanks, and both these are exposed to the atmosphere. So, both of them are experiencing atmospheric pressure. So, that is why P1 equal to P2 equal to P atmospheric, where we are also assuming the rate of change of this fall of the liquid level in these 2 tanks to be very, very small. So, that is why we are taking the velocity of fall to be 0, and with this what we find that this is the expression for the head developed. Now, for this loss of the head in the pipelines and fittings, we find that for all the bends and valves and whatever we have given in the problem, we write these expressions, and these expressions, you can see these expressions are written for the suction side and delivery side for the various types of fittings, and these are for the pipelines. And in this case, we have been given that the delivery side and the suction side diameters are the same, and we take it to be d, and the delivery side and the suction side diameters are same, and the flow rate is also same. So, the velocities will also be the same. So, we take them to be v. So, Vs equal to Vd equal to v, and then when we plug in these things, we simplify this expression for the head loss like this. And when we put this V in terms of the Q by A, volumetric flow rate divided by the cross sectional area. So, we get this expression, and then we plug in all the values which are given in this particular problem, and we can easily find out the relationship between the head loss and this thing, and then we put this value over to this expression, and what we get? We get this value of the head generated by the thing, and this HQ when we plot, this gives us the system plot. As we learned earlier, this is a system curve. Now, what we do, this H, we are writing H by Q, and these 2 dashed curves are supplied. This curve is the efficiency curve. This is the H versus Q given by the manufacturer, and this is the one we have generated. This particular big dash lines, this is the one we have generated. So, as we learnt earlier that wherever our system curve intersects the HQ curve given by the manufacturer, this intersection point is defined, is taken to be the operating point. So, what we do that here, this is the this head H versus Q which we have there, and here we have find this is the particular value of the Q we read at the intersection. So, the dashed lines are given by the manufacturer and the solid line is generated by us. So, this is how we are able to find out the operating point of the this particular pump. And here we find at the operating point the head developed will be 56 meter, and that means the pump can raise the liquid up to 56 meter. And if I want to find out the efficiency of the pump, then we can just simply extend this vertical line up to the overall efficiency curve that is given by the manufacturer and read out from this particular axis the value of the efficiency, and we find that it is slightly more than 80%, that is it is about 84%. That means we can say this pump will be working at 84% efficiency with this flow rate and producing this particular head. And the power consumption can be found from this particular formula which I showed you in the theory, and this is we plug in the values and we get this is the power requirement by the pump. So, now what we do that when we talk of some commercial pipe, then friction factor is not generally specified. In that case, what do? Then we have to choose some appropriate correlation to estimate the friction factor, and one of these correlations is the Colebrook-White equation. This is expression here, and in this case is the roughness factor which will also be specified in the literature for a given pipeline. So, this is taken to be 0.045 millimeter, and we plug in the values over here and we get the Reynolds number, and we can find out that for different values of Q that will determine the Reynolds number. We get different values of the velocities, and we can find with all the corresponding to any Q, we can find the value of the friction factor, and similarly we can from our system curve we can find out the various values of the heads. So, what we essentially find in this table is this: as we change the flow rate and we find the head generated changes, and second thing what we find that in this case as the flow rate is increasing, what we find the head generated is also increasing. So, this is the significance of this particular table and this particular set of calculations. Now, we want to know that under this new condition, if we are not given the friction factor, how the pump will behave. Now, we have generated the HQ curve from this thing, and these are the supplied by the manufacturer. Again, we look at the point of intersection, and what we find in this case it is coming to 0.08. That means there is a slight increase in the flow rate in the pump, and correspondingly we find that this head has decreased from 56 meter to 53 meter, and it has increased from 0.077 cubic meter per second to 0.08 cubic meter per second. And what we also find that there is some loss of efficiency. It was earlier 84%, now it has come down to slightly by 82%. And the pumping power has also come down. It was earlier 53 kilowatt, now it has come to about 51 kilowatt. So, what we find that there is a 3.9% increase in the flow rate for approximately the same power consumption. So, the power consumption does not change much, but the flow rate has shown a slight increase. Now, we come to another problem. In this problem, it is quite straightforward application of the data supplied by the manufacturer. It is related to the selection of the pumps. So, here we are given in this particular problem various combinations of the flow rate and the head produced by the pump, and we have to suggest which pump we should use under these given conditions. So, here what we shall do that we shall be basically considering this particular chart which gives us the selection of criteria for the various pumps, and it is plotted with respect to the total head and the capacity. And we shall be, what we shall do, we will take one by one all these things. So, first we shall talk about the 5 gallon per minute, and the head is 7500 feet. So, on this x axis we shall be locating the flow rate at 5, and on the y axis we shall be locating the head, and wherever these two lines intersect, this one, this line and this one intersect, we shall see that which, now we see that this intersection point falls in this zone. So, in this zone what we say, that we are going to use a reciprocating pump. So, next we shall go to the second part. In this case the flow rate is given 50,000 gallon per meter and H is 300. Now, first we look at 50,000, that is here, and 300 feet on the y axis, it is here, and wherever these two lines intersect, this is the point where this is a centrifugal pump. So, in for this particular combination we shall be recommending centrifugal pump, and what we clearly see is there that for reciprocating pump the head is quite high, the flow rate is low, but for centrifugal pump the head has come down, but the flow rate has increased, and that is what we also learnt in our theory, that whenever we want high head at low flow rate, we can go for reciprocating. When we want high flow rate, high capacity, but low head, we go for centrifugal. Then next we come to the third one. In this case Q is given at 10,000 and H is given at 5 feet. So, again we locate this 10,000 on this axis and this thing, and we find that wherever they are intersecting, this is the axial flow. So, in this particular case we shall be recommending axial flow. So, we find that the head is very low, but the capacity is quite high. So, in this case the axial flow pump is recommended. Now, these are the few of the books from which you can know detail about this particular theories. Thank you.